Namaskar and welcome to StudyIQ. I am your friend Rahul Saigaonkar. Let's continue our discussion of NCERT Science series. As you all know, recently we began with the NCERT Science textbook for class 10. Here also we are following a similar procedure as we did with class 6, 7, 8 and 9. We will be doing a chapter by chapter analysis. In our latest discussion, we discussed chemical reactions and chemical equations. We understood what are the different kinds of chemical reactions and how do we represent them in equation form. Today, we'll move ahead and discuss chapter 2, that is acid, bases and salts. For this, we have already established some base knowledge from our 7th discussion. When we discussed textbook for class 7, we understood some of the nuances about acids and bases. Today, we'll talk about different salts as well. So without any delay, let's begin our interaction. But before that, there is a small notice for all of you. If you're preparing for UPSC Civil Services examination, then today is the day, last day to enroll for our P2I batch because the admissions are closing from 12th July. There has been tremendous response, so the batches are closing fast. There are limited number of seats. You have opportunity just for a few hours now. Enroll. I'll see you in the class. The question is, why should you enroll for this? Because this is the most comprehensive program where StudyIQ will be hand-holding you through your prelims, through mains, and through your interview phase as well. It has been priced at a very affordable range, and for maximum discount, do use my code Rahul Live whenever you check out from the website or the app. Do it soon. Right, let's talk about acid, bases and salts. As I told you, the NCERT starts with you have learned in your previous classes. It means in the 7th class, we discussed about acids and bases. So let me give you a small or a quick recap of what we discussed because it's the continuing knowledge itself. So during our class 7 interaction, we understood regarding the tastes of acids and bases. Right? We asked the question, can we taste every substance to identify its nature? We said, of course not. We need some sort of method or mechanism using which we can identify the characteristics or the natures of those chemical compounds. And we came up with those also. But in general, we understood that bases are a little soapy when you touch. Bases are bitter in taste. Acids are more thick and acids are sour in taste. So we established these things. In nature also, we find acidic material. For instance, in our day-to-day products which we use in our kitchen also, like vinegar, like the citrus fruits, like curd, spinach, they contain many acids. Vinegar contains acetic acid. And when it stings you, it releases formic acid into you. Citrus fruits, they contain citric acid. Spinach contains oxalic acid in it. Curd has lactic acid in it. Very similarly, there are many bases that we find. For instance, in lime water, we have calcium hydroxide. In different soaps, we have sodium hydroxide or potassium hydroxide. Milk of magnesia, it was predominantly used, or I can say it is predominantly used as a solution for acidity. And we also established some of the characteristics of acids and bases. We established that acid, they taste sour. When acid is touched with a blue litmus paper, it turns that litmus paper into red or pink. Acids also react with metals to give a salt and also release hydrogen gas. Acids are corrosive. Acids tend to corrode. That is why I told you during that interaction also, be very safe when you're touching acid. And acids produce hydronium ion. Acids basically produce H plus, or the hydronium ion in aqueous solution in water, it produces the hydronium ion. We had established these things. Apart from that, bases, they taste bitter. Bases, they turn the red litmus or the pink litmus paper into blue. Bases, they feel soapy. That means at your home, you have your bathing soap or you have a detergent soap, they are soapy, they are basic in nature, and they neutralize acid, of course. And in an aqueous solution, in water, they produce OH minus 1 ions. And through this interaction, through this basic understanding, we'll move forward. We'll talk about different kinds of acids and bases. Now, this has been discussed in the 10th in very short, but let me just give you some overview of how do we classify different acids and bases. Acids and bases both are classified first on the basis of their occurrence. They're classified as organic and inorganic. Organic means one that occur naturally. Organic acids are the ones which occur naturally. Inorganic ones are the ones which we produce in our laboratory. For example, say HCl, hydrochloric acid, H2SO4, sulfuric acid, nitric acid, all these are inorganic acids that we use in our chemical laboratories for testing. Natural acids, on the other hand, they occur naturally. In nature itself, there are different neutralization mechanisms. There is an example given here of nettle plant, nettle herbaceous plant, which has that acid producing mechanism. A nettle's sting, it has methanoic acid in it. Similarly, ant sting, it has formic acid and methanoic acid in it. Lemon has citric acid. Curd has lactic acid. I told you these are all organic acids which are found very naturally. In tomato, you have oxalic acid. In tamarind, you have tartaric acid. Orange has citric acid. Citrus fruits have citric acid. Vinegar has acetic acid. I told you this. So similarly, on the basis side, on the basis of occurrences, we have organic bases and inorganic bases. Inorganic bases, again, that we use in our lab, that is sodium hydroxide, potassium hydroxide, calcium hydroxide. There are many organic bases as well which occur in, say, our human body itself. There are many other organic chemical compounds which have basic nature. Apart from this, we also categorize acids and bases depending on their strength. Now, what is the meaning of this strength? Strength means when I put acid or a base in an aqueous solution, what kind of characteristics do they show? If an acid is strong and I put it in aqueous solution, say if I add acid into a water, it will completely hydrolyze. That means it is going to give you H plus ions and the corresponding conjugate base or conjugate compound. Similarly, for the bases as well, when I put it in water, it has to hydrolyze completely and give you OH minus ions. If they are not able to hydrolyze, then it becomes a weak acid or a weak base. For instance, many of the organic or the natural occurring acids, they are actually weak acids. For instance, these that I discussed with you, the acids that we discussed just now, I gave you example of the naturally occurring, right? Vinegar, acetic acid, all these are weak acids. Strong acids are the ones which inorganically produce HCl, H2SO4, they completely hydrolyze. In your aqueous solution, they give you H plus ions. Apart from that, both strong acids as well as strong bases, they form or they become very good electrolytes. This is a very important point. They become very good electrolytes. For electrolysis, we can use them. The third way of categorizing acids and bases is based on the concentration, that is the amount of hydrogen ions, here amount of H plus ions and amount of your OH minus ions present. That way we categorize them in concentrated and dilute acids, concentrated and dilute bases. Again, if something is concentrated, it will be corrosive. For instance, if there is a concentrated acid, you do not even touch it. Many times on these concentrated acids, there is always a warning sign that it is concentrated and you are not supposed to touch it with your bare hands. If you touch it, that is going to harm you. It is going to corrode. It leads to corrosion and erosive action. Same case with the bases as well. But acids are more severe. All right. So this is the categorization. Apart from that, in our 7th standard discussion, we established the concept of indicators. Right? That is what we saw. We said that it's not possible for us to taste each and every equipment or each and every chemical, I would say, not equipment, each and every chemical and tell the taste. If it is bitter, if it is base, if it is sour, it is acid. We cannot do it. That is why we come up with indicators. So we discussed some of the indicators, right? We discussed some of the natural indicators like the litmus. Litmus is a natural dye which is obtained from lichens. And litmus paper, if it is blue, when I put it in acid, it becomes red. If it is red, when I put it in base, it becomes blue. Apart from that, we also saw turmeric. Turmeric is also a very good indicator of especially basicity. Turmeric itself is acidic in nature. So if we add acid to it, it remains yellow. but it is a very good indicator of bases. When a base is added to turmeric, it becomes red, it becomes vermilion color. That's why we also establish, if it is a white shirt and you are, say you are in a function, you are eating somewhere, and some of the food, it falls on your white shirt, it is likely that the uh, the uh, the stain that is left out, it is yellow in color, but as soon as you wash it, it becomes red in color. Why? The turmeric in that food, it has reacted with the base and it has turned red. Apart from that, we also spoke about China rose or the gudal, right? So we also discuss some of the synthetic indicators, we'll talk, but in this NCERT, we categorize indicators into three different dimensions. First is natural indicators. We discussed this. Litmus is a natural indicator which is obtained from lichens. Turmeric is a natural indicator. China rose is a natural indicator. There is another natural indicator which is red cabbage juice. You take red cabbage juice, it is originally purple in color. You know it is purple in color. But this red cabbage juice, it turns reddish when it is touched or when it reacts with acid, and it turns greenish when it reacts with a base. So it becomes a very good natural indicator. Apart from this, synthetic indicators, we had discussed about this. We have created many synthetic indicators like phenolphthalein, methyl orange. Phenolphthalein is generally colorless. That means in acidic medium, it remains colorless. In very extreme acidic, it becomes orange color. In normal acidic, it becomes colorless. And in basic, it gives you pink color. And if it is a very, very strong base, then it becomes colorless again. Methyl orange in acidic pH, it gives you red orange color, but normally it has yellow color. In base and in neutral pH, it is yellow in color. So we have created some synthetic indicators as well. Apart from that, we also have another category, that is olfactory indicator. Olfactory indicators, they become very important, especially for disabled, to identify. Olfactory indicators are generally natural. We have natural olfactory indicators like onion. You have a characteristic smell of onion, right? And that characteristic smell, when it is added with acid, it does not change. But as soon as you add a base to it, onion loses its smell. It loses its characteristic smell. Same thing happens with vanilla. You know vanilla smell, vanilla ice cream, the vanilla essence. The smell of vanilla, it completely vanishes when you add with a base. But it smells, smells like vanilla itself if it is added with acid. As I told you, olfactory indicators are very important, especially for the disabled people. They can just smell it and sense it. Olfactory means where you can identify using smell, your senses, olfactory senses. All right. So we discussed about acids, we discussed about bases, and we discussed about indicators as well. So this is a gist of indicators that we discussed. Red litmus paper, blue litmus paper, they turn opposite whenever added with acids and bases. Turmeric is generally yellow, but when we add base to it, it becomes a reddish color. That's why color changes. Red cabbage juice, generally it is purple, but when we add acid to it, it becomes reddish. When we add base to it, it turns greenish yellow. Phenolphthalein, it is colorless in acids. It is colorless in acids, but it turns pink in bases. Methyl orange, onion, vanilla. When you add a base to it, its smell completely vanishes. Now, since we established idea of acids and bases and indicators, let's now talk about chemical properties of acids. Right. Acids, how do they react with metal? How do they react with other oxides? How do they react with carbonates? Common compounds that we find in our everyday life. First thing, reaction of an acid with metals. Now, when acid reacts with a metal, it leads to formation of salt, a salt, and remember, hydrogen gas is released. I can give you so many examples. Magnesium reacting with hydrochloric acid leading to magnesium chloride salt, and hydrogen gas is released. Calcium with hydrochloric acid, calcium chloride, hydrogen gas is released. Calcium with nitric acid, calcium with sulfuric acid, its corresponding salt, calcium nitrate, calcium sulfate is formed, and hydrogen gas is released. So when you add acid and a metal, a salt is formed and hydrogen gas is released. How do I identify this hydrogen gas? Hydrogen gas can be identified by simply burning it. You simply hold a candle at the outlet here. Hydrogen gas burns with a pop sound. So you identify hydrogen is released. So first thing we have established, acid plus a metal, it will lead to a salt plus hydrogen gas is released. Next reaction. How do acids react with carbonates and bicarbonates? See, whenever there is a metal carbonate, that means metal carbonate, when you add with acid, you form a salt. What is a salt? We'll understand that. We'll understand the definition of a salt also in the latter part of our discussion. There is formation of water and there is release of carbon dioxide. There's release of carbon dioxide. So when acid react with carbonates, it produces a salt, it releases water, and it releases carbon dioxide gas. How do we establish it, or what are the examples? Now you can see here, I can get sodium carbonate, I can get calcium carbonate, I can add it with hydrochloric acid. A salt is formed, sodium chloride or calcium chloride, water molecule is formed, and carbon dioxide is released. Now, how do I identify that carbon dioxide is released? One of the simplest methods is to check the outlet for carbon dioxide gas, is to take a candle and light the candle and hold the candle there. If the carbon dioxide gas comes, then the candle will get off, because combustion runs because of oxygen, and if oxygen is not available, carbon dioxide is continuously coming, then the candle will be off. But another method, chemical method, is mentioned here. Through this test tube, we can see carbon dioxide will be released, and in this test tube, we have calcium hydroxide solution. Now, when carbon dioxide reacts with this calcium hydroxide solution, it is also lime, basically lime, it forms a precipitate. It forms a precipitate of calcium carbonate. And if I continuously pass carbon dioxide through it again and again, then calcium carbonate also transforms into calcium bicarbonate. So first it becomes a precipitate, then again it turns into a colorless liquid forming calcium bicarbonate, calcium hydrogen carbonate or calcium bicarbonate basically. All right. So similar reactions, when acid reacts with carbonates or bicarbonates, it basically forms salt, water with the evolution of carbon dioxide. This is the example. Sodium carbonate mixed with hydrochloric acid, sodium chloride is formed, carbon dioxide gas is released, water liquid is formed. Similarly, if I take a bicarbonate, that means metal hydrogen carbonate, here sodium bicarbonate, sodium hydrogen carbonate, when I add with hydrochloric acid, you will get salt, carbon dioxide gas is released, and water liquid is formed. Right? So this is the reaction of acid with carbonates and bicarbonates. The next kind of interaction, acid reacting with a metal oxide. Now, only metal oxide is being discussed. Try to understand, acid does not react with a non-metal oxide. The reaction is fairly simple. Acid, when it reacts with a metallic oxide, it forms salt and water. Now I'm thinking, I've seen this kind of reaction somewhere. Say, when I add acid, when I add a base, what would it lead to? It leads to formation of a salt, and it also leads to formation of water molecule. Oh, that means it's basically some kind of a neutralization reaction. What do I understand from this? Why does this happen? Because metal oxides are basic in nature, and non-metal oxides would be acidic in nature. So do you recall this? We had discussed this when we spoke about metals and non-metals. In fact, all these ideas have been discussed once when we spoke about metals, non-metals, and their reaction with acids. It's more like a revision for us. Do you recall this? That metal oxides are chemical compounds that contain metal and oxygen atom, and they are basic compounds. So when I add this basic compound and acid, what will happen? Simple, salt and water will be formed. That means acid and base would be neutralized. That is why metal oxides, they react with the acids to form this, and these metal oxides are generally ionic compounds. They react with acids forming salt. And of course, when they react with water, they form basic solutions, basic aqueous solutions. Yes. Similarly, non-metal oxides, they are acidic compounds. And when I add this with a base, they both will neutralize each other. That's why this kind of reaction. I hope it's clear. One of the examples is here copper oxide, which is a black metal oxide added with hydrochloric acid. It leads to formation of copper chloride and then water molecule. One of the examples. Right? All right. Now, this was the reaction of acids. Let's now move to chemical properties of bases. Now, how does a base react with a metal first? How does a base react with metal? First of all, you need to remember bases seldom react with metals. But there are some metals like zinc. They are amphoteric, meaning zinc can react with acids as well. Zinc can react with bases as well. But in general, metals, they do not react much with the bases. One of the exceptions is zinc. So zinc, when added with sodium hydroxide, it forms a salt. It forms a salt and it leads to release of hydrogen. And this, through this reaction also, I can check how hydrogen comes. I simply hold a candle, I light it, you will hear a pop sound of hydrogen burning. Apart from this, how do bases react with non-metal oxides? We discussed how acid reacts with metallic oxides. Exactly that. Base, when added with a non-metal oxide, it leads to salt and water. Why? Because non-metal oxides are acidic in nature. Can I find one of the classic examples of non-metal oxide? Non-metal. I take carbon, add oxide to it, carbon dioxide. Carbon dioxide. Now, what is carbon dioxide? Carbon dioxide in general is acidic. You do know that if I add carbon dioxide with water, it leads to formation of a weak acid, carbonic acid. So carbon dioxide is acidic in nature. When I add acid and a base, it leads to salt and water. Simple example, sodium hydroxide, it creates or it gives sodium carbonate along with water when you react that with carbon dioxide. Apart from this, we have discussed neutralization reaction. How do acid and base react? Acid and base, they react to form salt and water. This is the basic neutralization reaction. Now, what do we have common between these acids and bases, or how can we define them? How do I understand what strength an acid has or what strength a base has? What is the concentration of acid and base? We need to understand commonality among them. See, what is the commonality? Every acid, when I create an aqueous solution of it, meaning when I add it to water, it will give me H plus ion. Take any acid, H plus ion as a cation and anion such as Cl minus, NO3 minus or SO4 2 minus. You take any example, hydrochloric acid, sulfuric acid, nitric acid, you will find H plus ion. Similarly, when a base is added into aqueous solution, we get OH minus, and strength depends on this itself. How is it electrolyzing? If it happens completely, then it's a strong acid. If it happens partially, it is a weak acid. Correspondingly same for the bases. So what do we see? We see that hydrochloric acid or any acid for that matter, it always gives you H plus ion. Now, when it is in aqueous solution, we call it hydronium. Why? Because H plus, it reacts with water to give you hydronium ion. So when I write H plus or hydronium ion, both would be one and the same. Please note this. Similarly, when I have a base in an aqueous solution, it will always give me OH minus. So these ideas of acid and base, they have been further explained by different theories. But before entering those theories, we need to understand two more terms, especially connected to bases. Because with bases, we have a term called as alkali. Alkali. Now, what is this alkali? When you say something is an alkaline solution, means a base is soluble in water. Alkali is a base which is soluble in the water. That's why we say alkaline. The term alkaline is used. So difference between a base and alkali is just that if a base does not dissolve in water, it becomes base, and if a base it dissolves in water, it is called alkali, and that becomes alkaline solution. So what is the understanding? All alkalis are bases, but all the bases are not alkalis because all bases do not dissolve in water. Right? That's the basic difference between these two. And I spoke about some theories, age-old theories have been there, modern theories have been there, which explain the idea of acids and bases. As I told you, one of the earliest ideas is the Arrhenius theory of acid and base. Way back, if I'm not wrong, I think 1887, it came up. And Arrhenius' theory basically says if there is an acid in an aqueous solution, acid leads to formation of H plus and its conjugate. Same thing for a base, it leads to creation of OH minus in aqueous solution and its conjugate. The modern theories have been a little different. Modern theory is Bronsted-Lowry theory of acid and base. It states that if something is acid in an aqueous solution, it leads to creation of a proton and its conjugate base. Similarly, in aqueous solution, you have a base. When you have a base, you add a proton to it, you create a conjugate acid. That's the basic idea of the theories that are given. These theories are not mentioned in NCERT, but I'm just telling you so that you have an idea, especially about Arrhenius theory. If I simply have a statement, Arrhenius theory is connected to what, or Bronsted-Lowry theory is connected to acids and bases. And why are we talking about these? Because we need to understand how to gauge the strength or concentration of acid. For measuring the strength of acids, we have created scales. And that scale, we have created a scale, that scale is pH scale. pH scale, it's a logarithmic scale of calculating what is the concentration of H plus ions in a solution. H plus, or for that matter, if it is aqueous solution, it would be hydronium ion. So the formula for a pH scale is basically pH is equal to minus logarithmic H plus. Since it's a logarithmic scale, lower the value, higher the acidity. Higher the value, lower the acidity. So on this pH scale, on the logarithmic scale, we have created a pH scale which goes from 0 to 14. The value goes from 0 to 14. If the value is near to 0, that means it is extremely acidic. And if the value goes near to 14, it is extremely basic. Here, it's devoid of those H plus and OH minus ions are higher. Clear? There are some representative numbers which are given here. Gastric juice, that means in our stomach, the acidity is somewhere in the range of 1 to 2. Lemon juice has acidity of about 2.2. Pure water, it is generally 7. Pure water is neutral. Blood is also around neutral, 7 to 7.5 range. Milk of magnesia has 10 pH, right? When I talk about concentration, concentration means how much of hydrogen ions are concentrated, and concentrated acids are very corrosive, very dangerous. All right, right. Let's move on. Since we created pH scale, pH has a lot of significance in everyday life. All of us, we are very sensitive to pH. For instance, if I do not have food, say for 6 to 8 hours, then the amount of acid in my body would increase. It leads to acidity. Similarly, plants, animals, different organisms, they are very sensitive to pH. They are very sensitive to acidity. And if there is a lot of pollution in our environment, it leads to acid rain. Acid rain means precipitation whose pH is very low. Precipitation whose pH is lower than 5.6, it is called as acid rain. And whenever there is acid rain, it leads to lot of problems to plants, animals, humans, everybody. It erodes or corrodes the monuments. We have seen the Taj Mahal case. It leads to reduction of pH of the water bodies. What happens then? The aquatic animals, they would be troubled. It leads to reduced productivity of plants, because with the precipitation, there is a lot of deposition on the leaves, which leads to reduced productivity of plants. Similar case with the animals as well. Apart from that, pH in the soil is very important. NCERT asks the question, what is the pH of a soil in your backyard? If you do a testing of that, for ideal scenario, for ideal productivity, its pH should be somewhere within the range of 5.5 to 7, I would say 5 to 7. pH of 5 to 7 is actually better for plant productivity. But if it goes below that, soil degradation, the soil fertility is lost. Plants cannot produce enough food in acid soil. That's why it becomes imperative for us, it becomes imperative for farmers, for the government, for everybody involved to ensure that soil fertility or soil acidity is eliminated. Soil should not turn acidic. Soil should not turn completely basic as well. Optimum level should be somewhere between 5 to 7 pH. Apart from that, in our day-to-day life, in our digestive system, we have different pH setup. See, our digestive system, it starts with mouth. From mouth through the esophagus, it moves to stomach. From stomach, we have small intestine and we have large intestine. Now, when you look at pH of our digestive tract itself, mouth has basic pH. Stomach has highly acidic pH, and this slowly and steadily changes through the small intestine. We have duodenum, jejunum, ileum. The pH level, it goes on increasing. Since acidic, that means pH goes down. It reverses here. In small intestine, it is again basic, but in large intestine, it is again acidic. So if there is any change in this pH level in our digestive system, we face problems. As I gave you example, that if you do not have food continuously, say if you're fasting and suddenly you eat a lot of food, you might end up having acidity, and for that acidity again you have to consume ENO or you have to consume some other antacid to neutralize it. So in our day-to-day activities as well, pH is very, very important, because again without proper pH, we find that the GI tract, it gets upset, and to neutralize it, we take antacid, we take magnesium hydroxide, etc. Similarly, pH in our mouth, I said pH is generally around basic. Saliva itself is basic, but pH change in the mouth, it leads to tooth decay. If in my mouth the pH reduces too much, if the pH goes down somewhere around 5, right, somewhere below 5.5, then the tooth decay takes place. And why does that happen? That happens because of activity of bacteria and other microorganisms. Microorganisms, they break down the sugar and food particles in mouth after eating, and then it produces or it lowers the pH of your mouth. That leads to tooth decay. That's why it is said that after every meal to brush your teeth. Why? Because you would not want your tooth to decay. Apart from that, many plants and many animals have self-defense mechanisms through acids and bases based on the pH itself. Mainly acids. I gave you an example of nettle, a herbaceous plant which releases methanoic acid. Similarly, bee, we have a bee, right? We have honeybees. Honeybee, if it stings you, what does it release? It releases different chemicals which has different acids. There is phosphatase acid if a bee stings you. So there are self-defense mechanisms as well. All right, so pH is very important for all of us in our everyday life, in our day-to-day life. So do observe these things to your preparation. All right. Now, apart from that, the last topic of our discussion today is salts. Now, we established that whenever there is neutralization reaction, meaning whenever acid it mixes with base, they neutralize each other, it leading to creation of salts and water molecules. So salts are basically ionic compounds which are formed after neutralization of acids and bases. And generally, salts tend to be electrically neutral. They are electrically neutral. They form electrolytes. They are electrically neutral. Apart from that, the commonest salts that we have is sodium chloride. And from sodium chloride, or through reaction of sodium chloride or sodium chloride solution, we can get many other type of different solids, different salts and compounds that we use in our everyday life. But let's talk about some of the characteristics of salt first. Majority of salts that we find, they are crystalline in nature. You take example of copper sulfate, sodium chloride, any other salts, they are mostly crystalline. It's not necessary that every salt has characteristics like the common salt or NaCl. Many can be transparent or many can be opaque as well. But majority of salts, they are soluble in water. Why? Common sense tells me acid plus base, salt is formed and water is formed. So soluble in water. Solution of salt, it conducts electricity. That means it is a very good electrolyte. Please remember that solution of salt is a very good electrolyte. As I told you, salt can be transparent, opaque, it can be colorless, or it can be white as well. It's not necessary that salts always taste salty. By the name, it's a misnomer. You think that salt should always taste salty. It's not necessary. Salts may have different tastes. Some may be salty, some may be sour, some may be sweet, some may be bitter. And generally, salts are odorless. Especially neutral salts are odorless. Now the question is, how do we categorize or classify salts? Salts are classified on the basis of their families. And how do we define those families? Similar acidic or basic radicals, they are classified or they're put into same family. For example, we have chloride salts. Salts where you have chloride. For example, sodium chloride, calcium chloride, potassium chloride, they are under chloride family. They can be calcium family as well, meaning calcium salts with different conjugates. Calcium chloride, calcium sulfate, calcium nitrate, they come under calcium family. Zinc family, similarly, zinc chloride, zinc sulfate, they come under zinc family. What are the different classifications of salt? We have three major salts that are formed through chemical reactions. A neutral salt, by name itself, it's understandable. Neutral salt is created when a strong acid reacts with strong base, leading to creation of a neutral salt. So remember, strong acid plus strong base, where the pH is around 7, it is a neutral salt. Classic example being the one that we consume, sodium chloride, sodium sulfate, potassium chloride. These are examples of neutral salts. But salts can also be acidic. That's why I told you neutral salts are odorless, and other salts, they may have some kind of odor or different taste. Acidic salts. Now, how would acidic salt taste? They would taste sour. When would acidic salts be formed? Acidic salts be formed when a reaction happens between a strong acid and a weak base, leading to creation of a salt whose pH is less than 7. Example, ammonium sulfate, ammonium chloride. Basic salt. Now, basic salt would taste bitter. When would it be formed? It is formed when a reaction happens between a weak acid and a strong base, leading to its pH higher than 7. Sodium acetate, sodium carbonate, etc. are the examples. Apart from these three, we have two other classifications, although these are not mentioned in NCERT, but you need to know this. There can be double salts. Double salts are those salts that have more than one cation or more than one anion. Classic example being potassium sodium tartrate. Commonly we call it Rochelle salt. I'm quite sure you have Rochelle salt at your home. Rochelle salt box. It has potassium, it has sodium and other non-metallic elements. Then you have mixed salt. Mixed salt is a salt which is composed of a predetermined mixture of two salts. We'll talk about one of the mixed salt, that is calcium oxychloride. We also call it as bleaching powder. We'll talk about that. Now, from these salts, we talk about some of the most important compounds that we use in our day-to-day lives. The most important one is sodium chloride. Salt, we use it every day in our cooking. It gives taste to our food. It gives that salty taste to our food. And without that salt, food would rather be incomplete. Sodium chloride, it is also known as common salt or table salt. How is it formed? It is formed through the reaction of sodium hydroxide and acid, hydrochloric acid, meaning one base, strong base plus strong acid, it leads to formation of sodium chloride. Its pH is somewhere around 7. Sodium chloride, you do know that we use it extensively. But many a times from this sodium chloride or sodium chloride solution, concentrated sodium chloride solutions, we obtain many other kinds of salts and compounds. Let's talk about them. One of the compounds is sodium hydroxide. Sodium hydroxide is a strong base. How do we get sodium hydroxide? It is also called caustic soda. Sodium hydroxide, how do we get it? We get it through electrolytic decomposition of brine solution. Now, what is this brine solution? It is concentrated NaCl solution, meaning I have salt I create a concentrated salt solution and go for electrolytic decomposition. When I apply EMF here, what will happen? Salt plus water, and I'm providing electrolytic force here. Then what will happen? Hydrogen gas is released towards the anode, chlorine gas is released at the cathode, hydrogen gas is released, chlorine gas is released, and the solution that is left out, that would be sodium hydroxide. This entire process is called as chlor-alkali process. Why do you call it chlor-alkali process? Because chlorine is produced, chlor-alkali. You do know what is alkali? Alkali is a base which dissolves in water. Sodium hydroxide dissolves in water. Sodium hydroxide, also called caustic soda, it is used in many processes. It is used to produce soaps, it is used to make rayon, it is used in production of paper, other products like dyes, etc. It is also used in processing of cotton fabric, metal cleaning, etc. As I told you, it forms a very good electrolyte. It is also used in electroplating and electrolytic extraction. Sodium hydroxide. Apart from sodium hydroxide, another product, a mixed salt that we use regularly, is the bleaching powder. Bleaching powder is also known as chloride of lime, and commonly we use bleaching powder to bleach, to clean something. Its chemical name is calcium hypochlorite. Calcium hypochlorite, CaOCl2. In an aqueous solution, the bleaching powder will react with water and it releases chlorine, Cl2 gas. Whenever bleaching powder is added to water, it gives a very strong smell, that is the chlorine smell. But how do we get, or how do we produce this bleaching powder? Bleaching powder can be produced from slaked lime, that is calcium hydroxide, aqueous calcium hydroxide. When it reacts with chlorine gas, it leads to formation of bleaching powder or calcium hypochlorite. We use bleaching powder extensively in our day-to-day lives. Bleaching powder is used for cleaning our dirty clothes. Bleach, you must have seen that ad, right? You must have seen that ad. Vanish the white bleach. It says it has a lot of oxygen molecules. It has chlorine as well. We use it as a bleaching agent for cotton, for clothes. Bleaching powder is also used as oxidizer in many chemical industries. It is also used to bleach the wood pulp in creation of paper. You have white paper, exactly. So wood pulp is bleached with bleaching powder itself. It is also used as disinfectant. It is also used as disinfectant to clean water. Your drinking water, you can simply add bleaching powder to it, let the bleaching powder react, and chlorine is released. Oxygen is also released there, and you will find that germs die. Many a times when you go to swimming pool, you have a characteristic smell. There also bleaching powder is used because chlorine gas is the characteristic smell that you find in your swimming pools. Bleaching powder. Next, baking soda. Baking soda. Sodium hydrogen carbonate or sodium bicarbonate. Baking soda is a very important compound that we again get from another chlor-alkali process. How do we get it? We get it when brine solution, that is NaCl solution, when it is reacted with ammonia and carbon dioxide plus water is there, it leads to sodium bicarbonate. This is another chlor-alkali process where chlorine gas is formed. You have some other compounds also which are formed. The chemical name of baking soda is sodium hydrogen carbonate or sodium bicarbonate. Commonly we call it soda, we call it baking soda, we call it bread soda, cooking soda, bicarbonate of soda. There are common names, and it has been used extensively. It is used as an antacid. It is used to clean. It is used to clean utensils. It is used to clean your body. It is used to clean odor. It is also used as face and body scrub. It softens your skin. There are so many do it yourself, right, DIYs that you find with baking soda. Baking soda and paste, baking soda and Coca-Cola, baking soda and lime juice used for cleaning. It relieves skin from itch, from insect bites. It helps to relieve baby diaper rashes. It can be used as oven cleaner. It can be used to clean bathroom tiles, silver polish, right? It can be used as a drain cleaner also. Simply add baking soda and vinegar, your drain would be clear. You must have seen so many DIYs or so many examples of baking soda. Apart from baking soda, we also have washing soda. Washing soda is sodium carbonate. Washing soda It has two sodium ions and a carbonate ion, that is Na2CO3. It is white, it is crystalline, and it dissolves in water. It is manufactured by thermal decomposition of sodium hydrogen carbonate itself. That means it is basically produced from baking soda NaCO3. When you thermally decompose it, you get sodium carbonate or washing soda. And you do know washing soda has many uses. It has many applications. It is used in your washing powders. It is used for washing your clothes. It is used for softening of water. It is used as one of the ingredient, one of the reactants for production of glass. In glass production, washing soda is used. In production of sodium silicate, washing soda is used. For making paper, for making borax, for making soap powder, washing powder or sodium carbonate is used. It is also used to remove hardness of water. It also has a lot of applications in textile and other processing industries. Apart from this, there is one more concept called water of crystallization. Since we are talking about salts, many a times when we see the formula, the chemical formula for salt, in that we have the salt plus some water molecule. Such salts are called hydrated salts, although they look crystalline. One of the examples is this copper sulfate, right? We have this copper sulfate crystal which is blue in color. But when you see copper sulfate crystals, they are represented as CuSO4. This is the salt. Plus, it also has 5 water molecules. Yes, it is in crystalline form. Yes, you cannot see that water, but you can get a feel of it. When you simply heat this copper sulfate, these crystals, they become colorless. But again, when you simply add some water, when you hydrate them, they again become blue in color. That means in some salts, especially hydrated salts, there is already water present in them, and that water is called water of crystallization. That's it. Some salts combine with water and form hydrated crystals. The water molecules required to form these crystals, they are called as water for crystallization. In fact, many a times you do see during the rainy season, you have salt, but that salt, it has become moist. Table salt during rainy season, you must have seen table salt during humid days, or gypsum is another example where you have water molecules in it. So water of crystallization. One example of this hydrated salt is plaster of Paris. Plaster of Paris is produced from gypsum itself. Gypsum is this particular compound, that is calcium sulfate or hydrated calcium sulfate. It is called as gypsum. Gypsum can be naturally found. Now, when you heat gypsum, the gypsum get calcinated. That means some water molecule is lost. This solid gypsum, it turns into this powder called as plaster of Paris. And when you again add water to this plaster of Paris, it becomes extremely hard. That's why plaster of Paris has many applications. It is used in various areas. It is used for sculpting materials. It is used in your house, in your construction work, right? Plaster of Paris. POP is used for your walls, right? POP is used even for your ceilings, right? POP is used for making equipments like these. POP is used even for dental filling. Plaster of Paris is used for dental filling. It is used in soils, especially gypsum itself. Gypsum can be used in soil to reduce its acidity. When your bone is broken, or when there is some sort of fracture, you have a plaster. And what is that plaster? That plaster is plaster of Paris itself. So there are so many applications of plaster of Paris. You can use it for bandages, for plasters, for building material, for furnishing house, for finishing houses, for sculpting materials. So many applications of plaster of Paris. What is this? It is a hydrated salt, or it is prepared from hydrated salt. It is prepared through calcination of gypsum, simply heating or decomposing gypsum, where it loses some amount of water to form plaster of Paris. All right. So please remember these salts. Sometimes questions can be formed. For instance, if I have to create a simple kind of a question, I can give you the name of the salt, and say probably its application this side. application, and I can create a question where you have different pairs. For example, I say washing soda, I say baking soda, I say bleaching powder, and I simply give you the application of that, and I interchange them, and I give you a question where how many of these pairs are correctly matched and how many are not. So different kinds of questions can be created from this particular topic. Again, it gives you some basic knowledge about chemistry, basic knowledge about acids, bases, and salt. How do they react? And mostly regarding the salts and their day-to-day usage. Okay, right. That's it for today's discussion. Thank you for watching this video. And if you have liked this video, or if you have any queries, any doubts, any complaint, feedback, suggestion, you can always reach out to me on this particular ID at the rate Rahul Sai 222. You can message me on IG. I do respond on Saturdays and Sundays. Thank you for watching this. Jai Hind.